Okay, so this is your last note where you will just hear me and not actually see me, because hopefully at this point I will be coming back next week. So thank you for hanging in there, and hopefully everything is going well for you. So last thing we're going to talk about is called the kinetic molecular theory before I get back. And what it does is it tells us why gases act the way they act. Everything we have now is mathematical. It's very logical. It's very, I plug in numbers, I get a number. Kinetic molecular theory is much more about thinking, and it's I think for a lot of people a little more difficult because you have to think about why does something happen. And it basically tells us what are the molecules doing, and basically kind of explains what we're seeing mathematically. And this guy, this Rudolf Clausius guy, he's the one that came up with it. All right, so for you to have a kinetic molecular theory, you have to just agree with a couple things. So the first thing is that gases are made of molecules, there's a lot of them, and that they're going to be continually moving and they're randomly moving. They're not all going to spontaneously decide to attack you. They don't get together and have powwows and whatnot. And it is not like all the oxygen molecules decided to run away into a corner. That's the first one. The second one is that the actual space that the molecules take up is very small compared to the container it's in. So like right now, the container is this room, but it could be a container of a bottle, it could be a scuba diving tank, stuff like that. Third thing you have to agree with is that even though there are attractive and repulsive forces, most of the time they're negligible. 99% of the time, they're so minuscule that they don't matter. Number 4, there is energy transfer, but when they over time, the amount of energy is completely the same, and it's called perfectly elastic. So it's not like a car crash where two molecules hit each other and they fall apart and we lose energy. That doesn't happen. And then the last thing you have to agree with is that the kinetic energy of the molecules is proportional to its temperature. So the more energy something has, the higher the temperature is going to be. And if you're at the same temperature, you're going to have the same kinetic energy. And you just want to remember that kinetic energy, I'm not sure what encoder server quit means. We're having all sorts of problems. So kinetic energy, let's try this again. Kinetic energy is 1/2 mv squared. M is your mass, v is your velocity. So you may want to write that down if you haven't had physics or you just think you might forget. Okay, a couple of things that it helps to explain is why is there pressure exerted by gases? Well, this is because the gas molecules actually hit the walls and they apply a force. The more collisions there are, the more force, the more pressure. And the absolute temperature is basically the higher your temperature, all it is measuring how much average kinetic energy these molecules have. We're not saying that every molecule is moving at the same speed, but we're saying the average one works out. So if I double my temperature, my kinetic energy should double. And by doing that, if my kinetic energy would double, my collisions would increase because my velocity would go up, and I would have more pressure. So, do all molecules at a temperature move at the same speed? No. They have the same average kinetic energy, but not the same speed. If you took a picture, they can be moving at very different speeds. Just like if you're playing a basketball game, everyone's running at some point. But if I look at the basketball court at one moment, someone may be standing still. Someone may be running at an all-out sprint. So just because you take a snapshot doesn't mean we see the whole picture. But overall, the average is the same. And the higher the temperature, the more energy you have, the more spread out it will be because you have a larger range to work over. All right, and then the last thing before we try a couple of things to think about is what does the volume do? So if we don't change our temperature, our molecules are moving at the same speed. So if we have these molecules are moving at the same speed and now all of a sudden they have more volume to move, that means they have to go further before they have a collision. And remember, collisions has to do with pressure, so the pressure actually decreases. So that's why, as we said in Boyle's law, as your volume increases, your pressure goes down and vice versa. The opposite is what happens when we do change temperature. So if we change the temperature, now the molecules are going to be moving faster. They're going to be in that same space. They're moving faster. They're going to collide more. And that means the pressure is going to increase. So again, this is just helping us to explain what are we seeing with these laws. So what we're going to do is practice one, and then you're going to do one, and then that is that. Okay, so what we're going to do is say, are they true or false, and how do we fix them? So first one, a gas consists of molecules in ceaseless, ordered motion. We're hoping that you said that that first one is false. And the problem with it is ordered motion. It's not ordered, it would be chaotic. So you should write false. And it's random motion, all that kind of good stuff. Number two, these molecules, which mean gas molecules, occupy a large percentage of the volume of the container they're in, basically. So that should be false, and that's because this should say small. They don't take up much space. Number three, the time between collisions of two gas molecules is long compared to the time that the molecules are in contact. That would be, we're hoping, true. Gas molecules don't touch very often, so the time between collisions would be long comparatively. Number four, attractive and repulsive forces act between the molecules. This one's kind of an iffy one. You could go either way. They do act, but they don't matter. So you could kind of say true and false, but have no effect, really. That one's kind of a tricky one. And number five, the average kinetic energy of the molecules is proportional to the absolute temperature. And we're hoping for that one you would say true. All right, so what you're going to do is go to the next slide. You're going to try it on your own, work with a group or whatever, and then when you come back, we'll actually have the answers up there. Okay, so hopefully you're ready to go. So, how does the average speed of nitrogen molecules change if we increase the temperature? If we increase the temperature, the average speed should increase. So you should have increase, go up, whatever you want to say. Remember, they're directly proportional. That doesn't say goop, it says go up. Letter B, an increase in volume. So we have to think, does the increase in volume do anything to the speed of atoms? No, so there should be no effect. Letter C, what happens if we mix it with argon now? And the argon is the same temp. If they're at the same temp, that means there's no energy exchange or anything. And just because there's argon there doesn't mean anything will happen to nitrogen. So there should be no effect. D, if we mix it with argon but now it's at a lower temperature, that means overall temp will drop, which means the speed should decrease. So again, you have to think of this. This is not something that you just like, it's not a fact. You have to think. And that is it.